All right, so we kind of finished up with this here, doing our steric numbers and coming up with shapes of the molecules. Remember, that's the molecular geometry, what the actual molecule looks like. The electron domain, I like the word domain better because electron pair geometry is a little confusing because a double bond is considered one domain. Okay, so that's carbon dioxide. That has two domains. If you call it electron pair geometry, it's kind of like, oh, 1, 2, 3, 4. So I like electron domain geometry. That's what I learned in the book here is using electron pair geometry. I think that's more common now. The electron domain or pair geometry is just the regions around the central atom. So that's considered a single region, even though it's two pairs, double bonds. Okay. And when you have no lone pairs, then the electron domain or pair geometry and the molecular geometry are the same, right? The names come about as we get different numbers of lone pairs. Okay. Separate from this is the octahedral, which is the electron domain geometry for SN equals 6. Okay. And so if you have no lone pairs, the shape of the molecule is octahedral. But once you have one lone pair, it's square pyramidal. And I forgot my models. We had them the other day, but I forgot them today. In fact, heck, did I bring them back? I don't even know where the heck they are. They're back in my office. I don't remember seeing them. Maybe you probably took them. You already have your own set. You don't need them. All right. I don't know what the heck I said. Hopefully they're in my office. Anyway, so these different shapes come about, and really, since you don't have to memorize anything, everything's open book, open note. You'll kind of just refer to this once you figure out the Lewis structure to get your name, your shape, or your molecule. Okay, just be able to distinguish between electron domain and electron pair geometry. And then we did these three already. These are simple ones. And introduced us to this idea. All of these had steric numbers are 4 or less. You know, as you get into 5 or 6, you get a little bit more choices and things to do. So let's do these right here. Okay, let's start with the SCN negative one. How many valence electrons? Flush. How many? 16. Add 1 for the negative sign, right? We got sulfur 6, carbon's 4 is 10. 5 for nitrogen is 15. 1 for the negative sign, the ion, 16 electrons. What's my central atom? Carbon, of course. And now you could put 8 around each of the peripheral atoms. When you get good with this, you start to say, well, wait a second, I'm going to run out real quick. I'm going to have 16 and 16. I mean, I'm sorry, 8 and 8 is 16. I'll be done. And carbon will be left hanging with only 2, right? So you know right off the bat, I'm going to need at least a double bond, right? Somewhere. And nitrogen likes more bonds than sulfur. Let's start doing something like this. But of course, you realize you're going to run out of electrons still. That's still 16, right? And we still haven't satisfied carbon. So remember, the double bonds come in when you run out of electrons. You don't add double bonds if you have extra electrons, okay? Yeah, the extra electrons is when you put them on the central atom because you've got an expanded octet, right? You got an element that's in group 3 or lower that can handle those. So those are 2 things to remember. Double bonds kick in when you run out of electrons, when something's not been satisfied, and triple bonds, if you will. And then extra electrons, you just kind of throw them on the central atom. So this is not going to work. So we either want to put a triple bond over on the right there, or 2 double bonds. Try either one. I'm going to erase it. Whoops, that's not what I wanted. I'm going to erase a pair, and this is going to freak out on me here. Erase a pair of electrons here. And let's just try the sulfur and give that a double bond. Now that's 16. Everyone's got an octet. We probably should check our formal charges just to see what they look like. Remember how to do formal charges. It's the valence electrons, right? And I'm just going to do this. Valence electrons minus, it's going to be your lone pairs, right? I should say lone, I don't know how we, there's different ways of doing it. The lone electrons assigned to that, plus you can do either half of the bonded or just the number of bonds some people do. I think the book did it half the bonded electrons. So let's start with sulfur. Sulfur's got 6 valence electrons, right? So it's 6 minus, it's got the 4 and the 2, right? So sulfur is equal to 0. Everybody see that? What's carbon? Carbon's got 4 bonds. That's easy. It's 0. Okay. Carbon's almost always going to be 0, except for some sort of strange radical, something like that. It's valence 4. Half of all the bonded gives it 4. So that's going to be 0. What's nitrogen going to be? -1, right? Because it's 5 minus the 4 plus the 2. It's a -1. Now, it is the most electronegative element. So if you're going to have a negative, I've had a couple people zooming about, formal charges and things like that. If you're going to have a negative, it needs to be on the more electronegative element. And electronegativity increases up and over. Nitrogen is more electronegative than sulfur. And then, and of course, sulfur's further over. Okay. So you have to either look at your electronegativity chart or just know that nitrogen's, because the way it goes is fluorine's 4, oxygen's 3.5, and then chlorine and nitrogen are 3. And then everything else. That's kind of what I remember those. So I know nitrogen is the most electronegative, so that's okay. If we did move a triple bond over there and a single bond on the sulfur would then be 6 minus 2, 4, 6, 7. It would have a -1 formal charge if we did this. Whoops. Right? Nitrogen would be 0, which is better for nitrogen, but now you're going to have sulfur 6 minus 2, 4, 6, 7, a negative on the sulfur, and you don't want that because nitrogen's more electronegative. So that's how you know that this is the correct formal chart, a correct Lewis structure over here. Questions? We're not done. I'll make sure everybody's okay with the formal charge. Now, I should tell you, because this came up in a Zoom session the other day, formal charges are not the be-all to end-all. They will not lead you to the correct structure every time. There's more to it than that, okay? There's one on the practice exam that came up on the exam last year, unintentionally. I mean, it was not my intention, so I gave credit for 2 structures because the formal charges led you to the wrong structure, and I was not going to grade that as a wrong answer when you guys were told and you're being taught to use formal charges. But I want you to realize that as you get more experience, you move in the direction of taking organic chemistry and things like that. Realize formal charges is a tool, but it's not always the correct answer. There's other things to consider. Stability of the molecule and the way it's structured. And I'll talk a little bit about that when we do that review sheet. So if we're good with the Lewis structure, we got to get to the electron. I want to ask you the electron domain geometry and the molecular geometry, just for sake of completeness. So what is the electron domain geometry of this molecule? Linear. And what's the molecular geometry? Linear, right? It's got two domains, no lone pairs, linear, linear. Done. Is everybody good? Question. The CN ion, which you'll see sometimes, smart work, exam, back of the book, I don't know, is actually a triple bond. It has to be. The CN negative ion. Oh, by the way, if you're doing smart work and you have an ion and you keep getting the wrong answer, it's probably because you didn't put brackets and the charge. You have to do that. Okay, and a student that was having trouble with that couldn't get the right answer. They showed me their Lewis structure, and I'm like, that's fine. You didn't put the bracket.
How do you do that?
There's menus. I mean, I can go in there and eventually figure it out, but there should be a little thing that pops up that allows you to put brackets around it or something. Has anybody done this yet? Or have you figured it out? So where can you share?
Well, okay, so they do have, if you click on what you need, they have a video or like example of how to do every single thing. Because honestly, I did it like a week last week, so I kind of myself don't remember.
So did you say there's a video somewhere you can watch it?
There are videos and there are like examples how to do it. But I think with the brackets, I think you can do it yourself manually, and it should work.
And where are the videos? Are they right? Are they linked right there?
They're on Norton, yeah.
Okay.
So like it says help, and then it shows
Okay.
you how to do it.
Okay. I can usually figure it out if you just go in there. There's usually a pop-up menu, a pop-up window or something of a manual, because you'll need to figure that out for other stuff too. Like even the Lewis structures, putting the dots in and the bonds gets a little tricky until you get familiar with it. So don't leave that to the last minute. And you shouldn't be anyway. You should be working smart work all along. But there are little quirks and things. And open in smart work is that since the very beginning of smart work started, there is that assignment there. It's ungraded that shows you how to enter certain things. So look at that too. All right. So is there any more questions about SCN negative? Okay, let's do NO2 minus. I just realized we have 3 there because we got the SF5 plus I threw in there. All right, so we're going to do NO2 minus. How many valence electrons? 18 I came up with, yeah. 6 and 6 is 12, 5, 17, 1, 18. 18 electrons. Central atom. Nitrogen. Now, if I do 8 and 8, that's 16. I realize right off the bat, I'm not going to have enough for an octet, right? For nitrogen. If I do 8 around each oxygen, right? I'll have 16. I only have 2 left. So we're going to have 2 up here, or we're going to have at least that 1 bond there. That will give nitrogen, and of course, this is an ion. What's the formal charge on the oxygen on the right? 0. You get comfortable with these. Some of you are probably like, how'd they do that so fast? You get comfortable with this. When oxygen has 2 bonds and 2 lone pairs, its formal charge is 0. You'll just start to see that, just like water. Its formal charge is 0. Okay, so you don't have to calculate them all the time. On the left, it's going to be what? -1, right? And what's nitrogen going to be? 0. That's pretty darn good. You can't improve on that, right? You put another double bond there, that's just it'll make oxygen 0, but it's going to make nitrogen -1. And you don't want that because oxygen's more electronegative. So that's good. We're done with the Lewis structure. Questions on the Lewis structure. Electron domain geometry. And trigonal planar, it's got 3 domains, right? 1, 2, 3 domains. Electron domain geometry includes all the domains. It doesn't matter if they're bonded or non-bonded, right? The bonded, the lone pairs come in when we're interested in, the lone pairs don't come in when you're interested in molecular. And it's not going to be linear, it's going to be what? Bent. I drew it linear, the Lewis structure is fine, but that lone pair up there pushes them down to give it some room, sorry. And so you get bent or angular. Some people call it angular, you might see that, bent, angular. So we have trigonal planar electron domain geometry, or triangular planar, some people call it. These terminologies vary slightly from book to book or person to person. Just get the idea down, recognize it. So trigonal, triangular, planar, and then bent, right? So just picture this is the electron domain geometry, and you pull one of those off for the molecular geometry, and you have angular or bent. Question?
What is it for the SCM negative? What's the geometry for?
That's linear, we said. Linear, linear. What's your first name again?
Tommy.
Tommy? Who's Tobias? Oh, there you go. I just get these names in my head, but so you guys with the T's over there, I'll get that down. All right, we're good with an NO2 minus, SF5 plus. Electrons. $40, right? That's 7 times 5 is 35, plus 6 is 41, but then take away 1 because you got a cation. 40 electrons. What's the central atom? Really? You sure? Right. You'll believe some of the structures I'll get, and on non-multiple choice exams I used to give in the past. Some of the things you see are amazing. I've had hydrogens as central atoms with like 3 or 4 bonds. All right, so we got sulfur, and as Megan said, we got 5 single bonds. 8 times 5 is 40, right? Oh, we're done. I don't even bother with the dots. You know what to do, right? Do that 8 times or 5 times. 8 times 5 is 40. That's it. So we know the electron domain geometry and the molecular geometry will be the same because there's no lone pairs, right? And which is what? Trigonal or triangular bipyramidal, right? That bipyramidal one. The bipyramidal is the one with the 5, and the pyramidal is the tetrahedral electron domain geometry that loses 1 pair like ammonia. So you got 3 and 1. That's not bipyramidal, it's just trigonal planar. I mean, not trigonal planar, trigonal pyramidal or triangular pyramidal. Questions? Okay. Okay, so we've already learned about electronegativity. So that means if we got differences in electronegativity, we wind up with a pole, a dipole. It's a measurable quantity. So it's basically how it aligns itself and moves in an electrical field. Okay, so it's something that's measurable. This is really being applied to your molecular compounds, your covalent compounds. Okay, it's not appropriate to think about a dipole moment for copper chloride. Although you can find them, they're measured through spectroscopic studies in the gas phase. Okay, because remember, those are crystals. We're talking about an individual molecule and how it aligns itself in a field. Well, copper chloride doesn't really have an individual molecule. It's a crystal. Now it dissolves in solution, and of course, then it has a bunch of ions that, of course, are going to move great electrical fields. So we're really dealing with molecular compounds. Something like CO2, even though it has polar bonds, you can see it's kind of like symmetrical now, and you don't wind up with a dipole because they cancel each other out. That's the key. They've canceled each other out, so you don't wind up with a net dipole. Kind of like a tug of war, it's not going anywhere. They offset each other. Does that make sense? Now, water doesn't offset itself, and that's why it's critical that it's not linear. It's not drawn linear, okay? Because if you draw it linearly, it looks like it's got no dipole. But we learned from those lone pairs, and that's why it's critical that these lone pairs do this. They take up this space, right? They push the hydrogens down. I mean, water being polar is kind of the essence of life. That's why we look for water on other planets and things like that. We don't know of life any other way than with H2O, right? It's a great biological fluid. It dissolves tons of species, so it's great for removing waste. It's great for delivering things and saturating cells and organs and all of that. All right. So it has a permanent dipole. And these can be determined in electrical fields. You can measure the movement and how they align themselves and things like that. You can get actual numbers for dipole moments. Now, when you look at some of these ones that are done for compounds that are not really molecular and they're in a gas phase and they're spectroscopic, you'll see much higher numbers in this. But for us, solution chemistry, which is chapter 8, is really important. It's important for health, for biology, medicine. You got to understand aqueous chemistry, body solutions. It's important for environmental chemists like me. We do a lot of water chemistry, right? Aquatic chemistry. Other solutions aren't nearly as important unless you're, going into different areas of chemistry, like organic chemistry and synthesizing things and making materials and stuff like that. Then you're working with things other than aqueous systems. But aqueous are much more important for just everyday types of things. So we'll stick with that. And we'll see that HF has a pretty good dipole moment. Water does too. So does ammonia, and it starts to drop off. And you notice that when you get to something like this, it gets a lot lower. Things are canceling each other out, you see? So if you take physics, you do vector analysis, and you realize if you put this vector over here and sum it, and with this one, you'll wind up with a net vector in this direction that gives you that dipole. Here, well, and some of these are canceling each other out and fighting against that fluorine, so your dipole moment's a little bit lower here. Because hydrogen's electronegativity is, I think, only 2.1. So this is the slide that I came up with several years ago, and students have thanked me for this one because it really is something, in my opinion, that should be like a page in a textbook or a table in a textbook. And that is, which of these shapes are symmetrical such that if all the attached atoms are the same, you'll wind up with a non-polar molecule, even though you have these polar bonds. Okay, now all the attached atoms have to be the same, because if you take something like tetrahedral and I do this, you better believe that's polar, right? Because the chlorine's highly electronegative, those hydrogens aren't going to cancel it out. So that is polar. So if all the attached atoms are identical, then all of these are symmetrical. And you have a non-polar molecule, even though you have polar bonds. You remember, octahedral is the one, which I had my models with me, but that the same in all directions, right? It's got the axial and the 4 around the equator, it's the same. And same with triangular bipyramidal, it's got 3 around the equator and 2. But if you start pulling things off, you know, you get the square planar. That is, that's the octahedral one with 2 lone pairs. And that's very symmetrical. It's just got a square. You pulled off those 2 axial ones. That's very symmetrical. Tetrahedral is, of course, trigonal planar and linear. Those are obvious ones. Now, how polar are these things? Well, you don't have to be able to tell me what a dipole moment is. I couldn't tell you. That's something that's measured in the field. But it depends on the number, the type, and the geometry of the polar bonds. You know, how polar is this one here compared to one that has, 2 chlorines on it? That's not that critical, as long as you realize those are both polar. And then you can make some of the obvious observations that poles will cancel each other out, that type of thing. I'm not going to ask you, to put some in, in order of increasing polarity if they're very similar to each other, But the way to think about ones like this is almost like pulling a boat. Like if 2 people were on the shore and there was a canoe out there and each had a rope, and here's the canoe, and one person's pulling like this and one person's pulling like this. How's the boat move? It moves like this, right? That's the sum of the vectors. You bring this vector over, you bring this vector over here, you line them up head to tail, and then you sum the vectors. That tells you the direction of the motion. So when you take physics, you'll do some of that vector stuff. Okay. Predicting whether or not a substance is polar. Does formaldehyde have a permanent dipole? Well, do the Lewis structure. We've done this one, actually. We beat this one to death. Lewis structure is pretty straightforward. You do have a double bond, of course, for the oxygen. Is this going to be polar? Yes. Oxygen's pretty electronegative. Hydrogens are not going to cancel it out. It is symmetrical. If you draw it with the correct shape, it's going to look like this, trigonal planar. But these are small dipoles, and you wind up with that compared to this, which is a bigger dipole because that's more electronegative. Now, those 2 hydrogens will have some mitigating effect, but you've got a strongly electronegative oxygen there that's going to pull, so that's not going to cancel. Now, if you had chlorines down here, right, that dipole will be a lot smaller because chlorines are pretty electronegative. And if you have fluorines down there, your dipole would actually wind up being in this direction, smaller than the oxygen one with the 2 hydrogens. That's what I mean by just, reasoning through the electronegativities, but you don't have to be able to decipher, all these small little nuances of polarity. Questions? Okay. The large differences in electronegativities of carbon and oxygen means the polar carbon oxygen double bond gives formaldehyde a permanent dipole. All right, so now this is where I would stop chapter 5 if it was entirely up to me. But we still want to cover some hybridization occur in the departmental decision. I'm on the committee that decides this stuff, and I'm in the minority there. But anyway, some people do more than others. Some people probably don't do it. Just say the heck with it. But anyway, So valence bond theory merges quantum mechanics and Lewis model of shared electron pairs to explain molecular bonding. So if I have a magnet and I drop it in the middle of like a bunch of iron filings, little pieces of iron that are magnetic, of course. And what happens is they kind of arrange themselves around that magnet in a pattern. If you've ever done anything like this or anything like that, well, I mean, a class or something like that, where you get this kind of pattern that arranges. And that's the field, effectively the magnetic field. And electrical fields and magnetic fields are the same. We know that from physics, the same force, the electromagnetic force. You know, back 50 years ago, they had separate forces, electric force and the magnetic force. Now they've been merged. It's the whole idea of going, you know, to uncover one universal force, you know, merging gravity and all the other forces. You have the strong nuclear force, things like this. Now, if I bring another magnet close by, do you think that field's going to change? Of course, right? If I start bringing another magnet in here, it's going to start attracting and it's going to mess that field up. So that's the way you have to think about the idea that we've talked about atomic orbitals, right? And they're all very nice for isolated atoms, but as soon as you start forming molecules, the atomic orbitals aren't very much valid anymore, right? I mean, if I have, say, and I forget what's on this slide. Okay, I have nothing on this slide. Good. All right, so if I have a chlorine atom and a hydrogen atom with their atomic orbitals, and I bring them close to each other, just like the two magnets. Remember what these orbitals are. You know, they're energy fields, basically. They're calculated probability of energy states, if you will. So they're going to interact with each other. So you get the idea that these atomic orbitals really go completely out the window. And you form these new quantum electrodynamic fields that describe the molecule. Now, this theory here is going to stick with, like, this is the problem with this theory. It's going to stick with these orbitals still being attributed to individual atoms, which is the problem with the theory. So the next part of the chapter, molecular orbital theory, which we don't cover at all, is far superior to this. And that starts to treat them as orbitals assigned to the molecule. There's no longer any individual orbitals for each of the individual atoms, which makes sense, almost like the way metallic bonding works. The electrons are not associated with individual atoms in a metal. They're associated with the metal as a whole. We described it as a sea of electrons in which the electrons kind of flow, right? Same type of thing. Think of the molecule as a field in which the electrons, you know, vibrate as waves in different ways and can shift and all that type of thing, rather than thinking about it as individual atoms. But that being said, when you think about carbon having two 2s electrons, right, and two 2p electrons, how the heck does it form 4 identical bonds? When we know through experimental evidence that it forms 4 identical bonds. Of course it would, right? Each of those hydrogens are the same. Makes sense for the stability of the molecule to have 4 identical carbon-hydrogen bonds. How do you get 4 identical carbon-hydrogen bonds from that? Right? The s orbital is filled, and then you have 2 p orbitals. Well, if you throw them out the window and say, well, the atomic orbitals don't exist anymore, but what forms is a new field based on the same energies that were there before. What you do is you got 1s, we have 1s, not one s orbital. I don't mean a 1s orbital, we have a 2s orbital, right? We have 1 2s orbital. So we have a single, I'll say, s orbital, and we have 3 p orbitals. So we have 4 orbitals. You know, what happens? I don't know what happens. But ultimately, it's kind of like asking, like, no, it's not even like asking that, so I'm not going to even say that. But anyway, you have whole new fields that form. Let's just say that these new fields that form are kind of a mixture of the orbitals that were there already. So we wind up with four identical sp3 orbitals. We started with 3p. We still have the 3p, if you will, right? It's in the notation 3p and 1s. So we wind up with four identical sp3 orbitals. So all you're doing is taking the 1s, the single s, and the 3p's, combining them to get four new orbitals designated sp3. Once again, this is just humans' vain attempt to try to describe it, and we need to do this. It's not done. It's not done for no reason. We need to come up with models to describe things so we can make predictions. Well, someone says that we've got to design this new molecule and this is what we need, and we can say, okay, well, based on our models, these are your choices, right? These are the orbitals that are going to work for you. The elements are going to work for you because they have these orbitals that can help you build that structure that you need. So we're not doing it just nonsensically. But there's limitations, and we're not gonna pretend that you know what actually happens or talk about what happens. Just like I can't tell you what happens here with this field here. It just rearranges itself and you have a new field. Okay? Because of the interactions. There's so many interactions going on. So that's how you get four identical carbon-hydrogen bonds for methane. Now your book's going to take you through sp, sp2, sp3, and then this edition of the book stops, and I don't know why. If you're going to do this, why would you stop there? The other edition didn't stop, and they stopped. So if you look at page 218, I'm not going to stop because if I'm going to do it, I'm going to at least do it right. Okay, they only go up to sp3. Well, we just did Lewis structures up to steric numbers of 6, right? So let's add two more. Let's add sp3d and sp3d2, right? So now we can, because this can only handle steric number of 4. So we added D. Remember, you can only do that if you're down in the third period or below. You got d orbitals there, right? You got a bunch of d orbitals available to you. Okay. We don't have to use all 5 p d or all 5. We don't have to use all 5 d orbitals. Okay. We'll use one at a time. So effectively, we wind up with 2 more, if you will. So now we have sp, sp2, sp3, sp3d, sp3d2. And those are your steric numbers: 6, 5, 4, 3, and 2. Okay. Now, another limitation of this theory, let me just tell you, it doesn't treat bonded and non-bonded electrons any differently. Okay. So methane has 4 sp3 bonds, right? Or domains. So does water. It includes the 2 lone pairs. So here's the actual bonding. So the 1s hydrogen orbitals now come and overlap, and that's how you get your tetrahedral with 4 identical bonds. Number of bonds right here. See? So that means methane, water are going to be included in here, and even another one that's going to be linear, right? Okay. So basically, and we know that's not going to be the case, but this is designed a certain way to answer a certain question, and it has limitations. And then molecular orbital theory is going to come along and refine on that. We'll talk about sigma and pi bonds and higher order bonds, and you'll get all that in organic chemistry if you take organic. And if you're a biochem major, pre-med, any of that, biology major, chemistry major, if you're a biology major, you better take 2 semesters of organic chemistry rather than the baby organic. Because if you don't, you shoot yourself in the foot. for graduate school, things like that. I mean, I was a biology major. I took 2 semesters of organic chemistry. I don't have a chemistry degree, believe it or not. I have a biology undergraduate degree, a master's in environmental engineering, and a PhD in soil chemistry. So I don't have a fundamental chemistry, undergraduate degree. But the science has become so integrated that over the course of those 3 degrees, I took so much chemistry. But there's things that I do differently than a traditional chemist, and there's gaps in my knowledge that a traditional chemist doesn't have, but there's things in my knowledge base I know a lot more about. They don't know stuff that I've taken. So that's just the way it works. So the easy thing now, you've already done electron domain geometry, electron pair geometry. That's all you do for hybridization. So, and you usually ask the hybridization of a particular atom. So what is the hybridizations of the central atoms of NCl3? Well, we got to do the Lewis structure, right? How many valence electrons for NCl3? 26. 7 times 3 is 21 plus 5. Central atoms nitrogen. I'm going to throw my 3 chlorines on there. That's 8 times 3 is 24. I'm going to need a lone pair up here. That's got to be done because I've done enough of these. And I know nitrogen likes 3 bonds. And with a lone pair, it's going to have a formal charge of 0. And my halogens, boom, all have 8. They're all going to be formal charges of 0. What's nice about Lewis structures, you might say to yourself, man, he can give me anything on an exam. And you're right, I can. But now that you just did the Lewis structure for NCl3, you now know the Lewis structure for PCl3. You now know the Lewis structure for arsenic trichloride. You now know the Lewis structure for antimony trichloride. Not only that, you know the Lewis structure for nitrogen trifluoride and tribromide and triiodide, right? And you know the Lewis structure for phosphorus trifluoride. Get the idea? They start to look the same. You say, oh yeah, I've done one like this before. It's different, but oh yeah, that oxygen's gonna have a double bond. That's gonna get a formal charge of 0. Boom, boom, boom. So even though there is a huge number of Lewis structures, once you've done a bunch, they kind of like start to fall into place. It's like, oh yeah, I get this. I've done something similar. Okay, so we're asked, what's the hybridization for this? Discussing it. Yes, very good. What's your first name again? Oh, Abigail, you said that. What's your first name?
Talia.
What is it?
Talia.
Talia, that's it. Abigail's right. She's got sp3. What'd she do? She said, oh, I've got 4 regions. 1, 2, 3, 4. It doesn't matter. That's a lone pair. How do you get 4? Well, you can only have 1 S. And you can have up to 3 P's. So 3 and 1 is 4. sp3, you wind up with 4 sp3 bonds, just like water or just like methane, even though their molecular geometries are different, their electron domain geometries and hybridizations are the same. Is that a hand or just? That makes sense? Okay, so let's do SF6. How many total valence electrons? Six times 7 is 42, and 6 for sulfur, so it's in group 2, so 48. Should be easy, right? 6 times 8 is 48. 6 fluorines surrounding the central sulfur. It's going to have no lone pairs on the sulfur. 1, 2, 3, 4, 5, 6. That's octahedral electron domain geometry, right? The molecular shape is still the same. This one over here, the molecular shape was what? I didn't ask you that, but I'll ask you now. The one with the check mark here. What's the shape of that? Well, that's the electron domain geometry. What's the molecular geometry? Pull one of those off. What do you get? Trigonal pyramidal, like ammonia, right? Trigonal pyramidal. This one now is, what's the electron domain geometry? Who said it? Octahedral, a couple of people said it. Octahedral, 6 groups. Molecular geometry is the same, octahedral, because we have no lone pairs. We've run out. 6 times 8 is 48. You will see sulfur take on some lone pair extra ones, expanded octets, because it's in period 3 and below. You'll see that a lot with sulfur, selenium, arsenic, antimony, tellurium. You'll see them do this a lot. Tin, not as much. And what's the hybridization? sp3d2. Very good. Several people said it. We'll give you some credit. Okay. So really, it's not a ton to study. All you have to do, you don't have to worry about this. Studying this. All you have to do is know your electron domain geometries and count up. That's it. Your steric number. So just make a table where the all that's on one sheet. That's what I would do with your lone pairs and bonded pairs, the molecular geometry, the electron domain geometry, the molecular geometry, and the hybridization. And boom. I will tell you the exam's looking tough. Just being honest with you. It's simply because of what I told you before. It's just not so much tough as long, even though it's only 25 questions, because kind of each question's a new structure, as opposed to the way the practice sheet was done, which was 2 years ago, not last year. That's 2 years ago exam. We were given a molecule and they asked you like 6 questions on it. Now it's like, so I tried to I put on less Lewis structures than I normally would want to do, just because it was getting too long. Because it takes time to do a Lewis structure, I get that. But the last exam, I think I had people finish in 30 minutes, and someone else finished in like 30 minutes, at least in the class. I didn't pay attention to Zoom that much, but 2 people were done in like 30 minutes. But I never like time to be an issue. I don't want that to be the case. I mean, that's not what learning's about. It's not like your boss is ever come up to you and say, here, get me this project report in 30 minutes. Don't talk to anyone. Don't use any resources. It doesn't work like that, right? In the real world. So my advanced classes, my graduate classes, I always did open book, open note. And I like that better. You learn more. Or take home. You learn a lot doing take home exams, open book, open note exams. All right. What do we got left? Anything? No, we're done. Beautiful. Summary. There's not much to summarize. You got to do your VSEPR, right? Including bond angles and lone pairs, being able to recognize, hey, how the bond angle changes. Polarity of molecules. You already did polarity in chapter 4. And here we just applied it to the molecules. And then hybrid orbitals. Okay? I'm going to tell you this now. The exam's what? I'm not done with it, but this is what it's shaping up to look like. 8 Lewis structures. 5 VSEPR questions. So 8 Lewis questions, 5 VSEPR questions, 2 formal charge questions where they're specifically about formal charge, as opposed to you might need to use formal charge to, answer some of your Lewis structures or whatever. 5 questions on bonds. And what I mean by that is like electronegativity, angles, polarity, strength, size, repulsion, where we talked about how lone pairs repulse and more than bonded pairs, things like that. 4 questions on the polarity of a molecule. Is this polar? Which of these is more polar? That type of thing. What's that? 13, 7, 24. That comes out to 26. 13. Anyway, and 2 on hybridization. I think that adds up to 26, but anyway, the exam's only 25 questions. So we'll take a look. I got a couple of Lewis structures here I'm going to do that I had for some reason picked out or something. Check that. Let's do this one. CS2. You can take a minute to start to work it out among yourselves. So you notice no questions about lattice energy showed up because I tested it on the quiz already. So there might be one in there in that bonding section, which is ionic or which is something like that. I can't remember. I had an 8-hour in-class exam once where people came with hand trucks with crates of book, and the teacher brought, professor brought pizza for everybody who sat there for 8 hours and did an exam. It's like taking an MCAT or something. How long are MCAT exams? Who's a pre-med student? I know all of you are, right? Do you know how long the MCAT exams are? How many? About 8 hours.
7 hours without breaks.
7 hours without breaks. Anybody get it yet? What'd you get, Abigail? Very good. You do it that one?
Yes.
Yeah. So you should get this, and we can do it. So you start, you say, how many valence electrons? What do we have? 16. 6 and 6 is 12, and 4 is 16. Carbon's the central atom, so you're going to do this. And then if you started doing this, you'd run out, right? So the first thing you do is you get rid of one, put a double bond there, right? And you know what's the formal charge on that sulfur on the right? 0. Plus you still only have 3 bonds on the carbon. So you know the other sulfur is going to get a 0 also. If we just do the same thing. Now everything has a formal charge of 0. Carbon's got its 4 bonds. That's carbon disulfide. Okay. You good on that one? I got SBF3. That's antimony, so it's down there at atomic number 51. It's under carbon and phosphorus and arsenic. Group 4. You're allowed to talk to each other. You don't have to be super quiet. Anybody get it? Carter, what'd you get?
Single bonded. Two electron.
Very good. That was pretty straightforward, not too bad. So antimony then is in group 6, and it's got 2, 3, 4, 5. So its formal charge is going to be +1, right? But each of the fluorines is going to be 0. Do you have a question or? Okay. So if you did a double bond, then your fluorines would wind up being what? Positive, right? Because you'd have that. Fluorine be 7 minus 2, 4, 6. You'd have a +1. That's the most electronegative element in the periodic table. Is that a question now? Yeah. What's the matter? Oh, is it formal charge 0 and I say +1? Oh, what I say 6? Oh, okay, thank you. Yeah. It's got a formal charge anyway, 0, so we're done because they're all zeros. Yeah, I did the formal charge wrong on antimony. 2, 3, 4, 5. Yes, I said 6, I think. Yeah, it's in group 5, so it has a formal charge of 0 anyway. Questions on that one? Okay, I have one more. This one's a little bit bigger molecule. But what you realize is, and I've been nice to write it in a way that lends you to the structure a little bit. If I didn't write it like this, it could be problematic for you. So if I said CH3NO, that's the same formula, right? But I've written it in a way that lends you to the structure a little bit. And once you do Lewis structures for one central atom, you can expand it to having 2, 3, 4 central atoms and build bigger molecules. I think giving it to the way on the right would be unfair for you guys at this point. Because you might start doing this. And then you're going to get into trouble. What's that look good? Let's see. Yeah, that's pretty good. Just came up with a third structure for this thing. I thought there was two good structures, but there's actually, this one is fine, right? Oh, am I missing something? No. Nitrogen 0. Oxygen's 0. Carbon. Yeah, that's a third one. There's two from this. There's two possibilities. I'm thinking I'm going to get two different structures depending on who did it what. And then I just came up with this one too, which is pretty good. I will tell you that if you're torn between like a structure that's really spread out linearly, as opposed to one that has more branching, the more branched ones are more stable and more likely to be the correct structure. This one, it's not as big of a deal because it's tough to have a linear structure here when you've got 3 hydrogens, you know, that's going to result in. But sometimes you've got choices where it's like, well, you could string these 4 out as almost linear, or I could branch them more. The branching tends to stabilize the structure more. You'll learn that a little bit in organic. Doesn't mean linear molecules don't exist, and there's linear hydrocarbons that are hugely, with all the hydrogens off. That's what hydrocarbons are. If you look at them like octane, octane is just this. Keep going, 8 for 8 carbons. It's just a straight hydrocarbon chain. But when you look at the structure, it's actually like this. Each of these represents a carbon. The hydrogens are not shown. It is bent back and forth. It's not just straight. So you learn that in organic too, the structure of the hydrocarbons. So anybody get a structure for this one? Besides Abigail and Houston and Carter. Anybody else? What'd you get?
I got the one that you did, and then
That one too.
yeah, and then I had an oxygen in the middle, double bonded to a carbon, and then 2 free electrons on the carbon, and then a hydrogen attached to it. Double bonded to a nitrogen with 2 hydrogens.
So this here is a no-no. You don't want to have carbon with lone pairs on it, almost ever. Okay? Only in strange molecules, radicals and things like that, and other things in which that has, you know, been attacked and lost something. So that's not a real stable molecule because carbon likes 4 bonds, right? It is the backbone of things. So in this case, you don't need to do that. This one doesn't do that. This one's okay, right? Formal charges look good. Carbon's got 4 bonds. Nitrogen's got 3. Oxygen's got 2. Someone else give me another one that they did over here without it looking like this. Hersha. Yeah. Just give me the backbone. I know the lone pair. 2 hydrogen off of the nitrogen. Not like this, right? That'd be a no-no. That's very good. That's one of the ones, right? Of course, you got your lone pairs on there. Did anybody get the other one? There's another one. What's that, Andrew?
Carbon double bonded to an oxygen, also, and the carbon is also double bonded to a nitrogen. 2 hydrogens on the oxygen.
That's too many bonds on the oxygen. That's where you run into problems there. So, there's still another one.
Is this right?
Too many bonds on the oxygen. It's got 4 bonds.
Okay.
Yeah. So he's got one of the oxygen, got 4 bonds on it, which is the one Hershey did the one. That's not it. With the oxygen double bonded off. Put oxygen. Oh, wait, that's not it. Never mind. I think that's it. No, that's it. Why'd I have this one here? That's not a correct structure. What the hell is that? I had one. These are the two that don't violate anything. I thought there was, it's probably the one I'm thinking of. I thought there was an ether. Yeah, there's no way to do that one. So yeah, look for carbon have 4 bonds. Look for nitrogen have 3. Go ahead. Oxygen has 4 bonds. That's just a no-no. It's got 3 and 1 is 4. It's too many bonds for oxygen. It's a good shot though. Yeah, you don't want oxygen. You're going to avoid it to have more than 2 bonds. Nitrogen have 3. I mean, there's violations to that, of course. There's this. This is the ammonium cation, but it's a cation. It's taking on a charge because it's got this extra hydrogen. It doesn't really want it, but these are the things that happen depending on what the environment is, right? If it's an acidic environment, this is what happens. Those hydrogens have to go somewhere, they go here. But that's not, the most stable form of nitrogen. It's going to like to have 3 bonds. Yeah, I was thinking there was one because I was thinking there are 2 carbons. There's one with 2 carbons. So if you have 2 carbons with an oxygen, you can often do this. Depending on the rest of the molecule, but you can also do this. We've seen this, right? This carbon with the double bonded oxygen. Sometimes the oxygen is in the middle. Of course, you're going to have. So this is a structure right here, common structure. Right there, right? I drew it linear. It's not going to be linear. That's not the one that's up there. It's different. This is a different molecule. But I'm saying this is pretty common. You've got oxygen in the middle there, but you have like almost 3 central atoms. You have the carbon that's central to the hydrogen and the oxygen. The carbon over there it's central, and the oxygen that's kind of branching those off. Remember, this is water, right? You can replace those hydrogens with lots of things, right? And they can be methyl groups, CH3 groups. That's what you're seeing up here. It's still going to be big. It's going to be 2 big methyl groups rather than 2 hydrogens. Yes, Mary.
I think I answered my own question. So oxygen doesn't get triple bond because if they only have 2 pairs of 1. So
Right. Right. In general. Okay. There's exceptions to everything in chemistry. But in general, right, you're looking for oxygen to have 2 bonds. Sometimes you'll see it have 1 bond more than you do see it have 3 bonds. Another thing you see a lot of, is that a question? Another thing you see a lot of is the hydroxyl groups hanging off. Like that. This is a hydroxyl OH group. This makes it an alcohol or an acid or a base, depending on the organic chemistry you learn. But you'll see that a lot, OH groups. That makes sense. The oxygen's got its 2 bonds. It's got this hydrogen hanging off, and it's bonded to the carbon. So sometimes you'll see what are called isomers, which are compounds that have the same exact formula, right? But they have 2 possible structures. Okay. So you'll see that a lot with things like this, where you can either put the oxygen in the center or have an OH group off like that. You'll see that a lot. And if you're asked to do a Lewis structure, they're both correct. Yeah, you could do that with this right here, right? Take this one. right here, which is what? The formula for this one is CH3O CH3, right? That's take that same structural formula and do this. Right? Same formula, CH3, CH3. All right. This one is an ether. This one is an alcohol. This makes it an alcohol. That's ethanol right there. So if you had a beer last night, that's what you drank. If you drink methanol, well, we'll be taking you to the emergency room. And the only difference is methanol is CH3OH. One CH3 group instead of two. The difference of an electron, a simple molecule, can change tremendously the reaction, the behavior, the toxicity. So this right here, chromium 6+ and its compounds are carcinogenic. Chromium 3+ is an essential micronutrient. 3 electrons. That's the only difference. That's how important electrons are, structures, right? Things like that. And it has to do with the way it behaves in the body. That +6 behaves very differently than the +3. All right. I'm done.